Hi, scared of the whole limit definition of derivative. The limit plus delta x all over delta x. Well, let's try to look for some pre-calculus last year. But if we're doing the limit definition of derivative, this is what I'm going to call it when you have to use it. And there will be times on the test where you have to use the limit definition of derivative. And on the AP test, they will require you to be familiar with it and know it and use it and identify it. So we'll talk more about that. So we're not totally getting rid of this, but we're just looking for some shortcuts so that we can use the derivative with other applications and not have to spend all of our time doing algebra. So if you do the limit definition of derivative, the derivative of x is just 1. The derivative of 2x is 2. The derivative of 3x is 3. So I'm skipping all the work to get from the function to the derivative. We're just looking at the answers. Okay, let's back up. We don't want to do this yet. So do you see a pattern yet? What if we have a linear function where x is to the first power? Notice what the derivative is. What do you think? Looks like it is the slope, right? Just the constant in front. The derivative of 1x is just 1. The derivative of 2x is 2. Derivative of 3x is 3. All right, let's look at quadratic functions. The derivative of x squared is 2x. The derivative of 3x squared is 6x. The derivative of negative 4x squared is negative 8x. Do you see a pattern in that? Notice this 2 became the coefficient and the power went down to a power of 1. What if we make this 2 the coefficient? There's already a 3 there. So what did we do with the 2 and the 3? Multiplied them. And the exponent went down to 1. Take that power of 2, put it out in front as the coefficient. 2 times negative 4 gives you the negative 8, and the power goes down to 1. So there's our pattern for x squared. Do you think that same pattern works for x cubed? Well, the derivative of x cubed is 3x squared. So what happened? Did that power go down as the coefficient? It sure did. What happened to the exponent? It was a 3 and it went down to a 2. Here it was a 2, it went down to a 1. So it looks like the power decreases by 1. What about this one? The actual derivative of g of x is 6x squared. Does it follow the pattern? Put the 3 out in front. 3 times 2, that gives you the 6. Decrease the exponent. Subtract 1 from it, you get x squared. Yep, looks like it works. Now let's use what we know about constants. If we're finding the derivative, we're just finding the slope, right? What's the slope of a straight, flat line, horizontal line? It's 0. What's the slope of this horizontal line? Still 0. So can we come to a conclusion about that? The derivative of any constant is just going to be 0. So we've got a few patterns and relationships, and mathematicians did this a long time ago. You're not the first to try to find shortcuts. So I'm going to summarize them in the next page here. C represents a constant, n is an integer, a number, positive, negative, 0, x is a variable. So if you want the derivative, remember this is the notation for derivative of whatever's inside of here. So the derivative of a constant is just 0. That's like the last 2 examples we did. And this is the biggie we're going to use a lot. The derivative of x to a power. You take that power and put it out in front as a coefficient, and you subtract 1 from the exponent. The derivative of x is just 1. We did that on the very first example. The derivative of a coefficient times whatever function, so if there's a coefficient out in front times a function, it's just that coefficient times the derivative of that function. So c times the derivative of that function. So we can use all these other rules to get the derivative of the function, and then if there's a constant out in front, just multiply it times the answer we got. Derivative is distributive in a way. If we want the derivative of 2 things added together, like if we want the derivative of x squared plus 2x, we can just find the derivative of the x squared and then find the derivative of the 2x and add those 2 together. So using this rule for the derivative of x squared, that would just be 2x x, because you put the power out in front. The 2 goes out in front, and you subtract 1 from the exponent. So the 2 minus 1 becomes x to the first, plus, and then the 2x, we're going to use this rule. We have a coefficient or a constant times our function. So it's going to be 2 times, and then the answer for the derivative of x. So we're using this rule. It's just 1. So I know a lot of rules to remember, but it's better than doing the long form. And if you ever forget the rule, you know, you can always go back and do the long form. But you're not going to want to do that. You do need to memorize these. You're going to use them a lot. Here's some trig ones. We're not going to talk about how to get them right now, but the derivative of sine is cosine, and the derivative of cosine, I have a typo here, is negative sine. The derivative of cosine is negative sine. Okay? Typo there. Sorry about that. So those rules you do need to memorize. We're going to use them a lot. Make sure you're familiar with them. Average velocity is delta S, and S is what our calculus book uses for position. I think in physics you might use X for position. We're using S. So delta S is the difference between two positions over the difference between the two times. So it's just like the old slope formula. Average velocity. It's not instantaneous velocity. This is instantaneous velocity. The derivative. So the derivative has lots of applications. The first one we talked about was the slope of the tangent line. The second one is the velocity. The derivative is the velocity. The derivative of the position function, s of t is the position function. The derivative of that function is your velocity. It's your instantaneous velocity, which is different than average velocity. Average velocity is something we could have done before calculus. Just subtract the two positions and subtract the time and divide the two. Just like slope. All right. Position function, you're going to have to be familiar with this because it's going to come up a lot in our calculus book. It's 1/2 times the pull of gravity. So it's either negative 9.8 t squared and then plus the initial velocity times t, so the velocity of the thing that if you just drop it, it's going to be 0, but if you shoot it out of a gun or out of a cannon or throw it, it's going to have some initial force to it. And then s sub 0 is the initial height. So if you drop it from a cliff, you need to know the initial height. But if you're just throwing it from the ground or kicking it, then the initial height is 0. So negative 9.8 is one of them, and then negative 16 t squared is the other. One of them is, negative 4.9, half of the pull of gravity. So this is when you're working in meters, and this is when you're working in feet. So 1/2 the pull of gravity is negative 4.9 meters, and then negative 16 is if you're working in feet, because negative 32 feet per second is the pull of gravity in feet. All right, so these two formulas we're going to use a lot. They may not give you the equation. Just be familiar with it and know it, even if they don't give it to you. All right, let's do some examples using our shortcuts. If you have a function like x cubed, you may need to rewrite it, you may not. This one we don't need to rewrite it because it's already in the form of x to the n. If possible, rewrite all your functions in the form of x to the n. So to differentiate it, we put the 3 out in front, subtract 1 from the exponent. So we have 3 times x to the second. That's your derivative. This one was pretty easy. You can skip this step if you want. Just put that out, the 3 out in front, and subtract in your head. That's fine. This one we do have to rewrite it. We want it in this form. We don't have a quotient rule yet. So if anything is in the form of a quotient, we can't take the derivative of it until we rewrite it. So we're going to rewrite this using that rule that says that if you have an exponent that's negative, it's in the other part of the fraction. So 1 over x squared really could be written as x to the negative 2. We're going to use that to take the derivative. So put the power out in front as the coefficient and subtract 1 from the exponent. Now careful, what's negative 2 minus 1? It's negative 3. And then you may need to simplify again to rewrite it. Negative 2 over x to the third is your final derivative. So you change the 1 over x squared, x to the negative 2, multiply the negative 2 out in front, and subtract 1 from the exponent, because the derivative of x to the n is n times x to the new power of n minus 1, whatever that n was. Okay, let's do this one. 2 times the square root of x. We want to rewrite that so it has a power. Square root is x to the 1/2. To take the derivative of a constant times a function, you take a constant out in front, and then you take the derivative of the function. The derivative of x to the 1/2 is 1/2 times x to the n minus 1. So you took the 1/2 and put it out in front, and then you subtract. That equals 2 times 1/2 is just 1, and then 1/2 minus 1 is negative 1/2. But we don't want to leave it with a negative power, so we want to write 1 over x to the 1/2. You can leave it like that, or you can write as 1 over x to the 1/2 in a square root, because 1/2 is the same as square root. Okay, how about this one? Rewrite it. 7 and 3 should stay where they are, but x to the negative 2 means it should be like this. The negative exponent should have been on top to make it a positive. So now we're ready to take the derivative, because it's in the form x to the n with a constant out in front. The 7/3 is the constant. So the derivative is 7/3 times times the derivative of x squared. So 2x to the 2 minus 1. So 7 times 2 is 14, so we have 14/3 x to the first. This one, that's like a negative 1/2 x to the fourth plus 3x to the third minus 2x. So if you want to think about that negative 1/2, it's not really a quotient because x is in the numerator. So if there's a constant that makes a quotient, that's okay. Just pull out the constant as the coefficient. So now we're going to take the derivative. Notice I don't have an equal sign here because I'm not writing something that's equal. I'm actually finding the derivative. So it's negative 1/2, and then times the derivative of x to the fourth, which is 4x to the third. That's 3 times the derivative of x cubed, which is 3 squared, and then minus the derivative of 2x. So it's 2 times, what's the derivative of x? Just 1. Derivative of x is 1. Put the power out in front, it's 1 times 1, 1 out in front, and then 1 minus 1 is 0 for the exponent, so x to the 0 is just 1. So there's your derivative of x is just 1. Now simplify it. Negative 1/2 times 4 is negative 2. So we have negative 2x to the third plus 9x squared minus 2. And finally, y equals x plus cosine x. We don't have to rewrite it. We're just ready to take the derivative. The derivative of x is 1. The derivative of cosine is negative sine x. So that's our full answer. All right, short video today. There's your homework, page 115, 1 through 29 odd. You can get started on it now and get the easy ones over with and work on the harder ones in class tomorrow. Have a great day.